In 3, 2. Well, welcome, everybody. Today we are very excited to have Adrian Popescu presenting their paper, Dataset Knowledge Transfer for Class-Incremental Learning Without Memory. Adrian is a researcher at the Université Paris-Saclay. Adrian, we are very excited to have you here to talk today. I personally find memory-free class-incremental learning to be an exciting and, more importantly, very challenging problem. So, without further ado, please go ahead and take it away.
Okay, thank you, James, for the opportunity. So this is some work that we've done last year. It was presented WACV at the beginning of 2022, and the idea is to see how we can improve memory-free class-incremental learning. So, I assume that you all know about what class-incremental learning is. I will skip this slide quite quickly. So the main problem that we have in class-incremental learning and more generally in continual learning is catastrophic forgetting. So basically, neural nets tend to forget what they learned before when they ingest new data and they model new data. So we have a small example here with an incremental learning with 9 states. And we plotted the mean prediction scores before softmax for new classes and past classes in each state. So what we can see is that there is a clear difference between new and past class scores, which basically goes to saying that past classes stand no chance if we don't do anything in terms of countering catastrophic forgetting. So what we try to do here is two things. So we remove the well-known distillation component, which we argue that is not that necessary or not always. And we start from the so we have this transit method, which is a layer which can be applied to different existing methods. So we tried it with 4 of them. We have 2 examples here. So we have learning without forgetting, which is very well known. We have also Lucy, which is also quite known. So it's a CVPR 2019. And we've done so we place ourselves in the final state, so in the 10th state. And we look at the mean and the mean prediction scores for the current state and for the previous states. And so what we see in terms of predictions is that they vary from state to state. And what is also important to notice is that the predictions for the past states, so from 1 to 9, they also vary quite a lot. So if we look at Lucier, the predictions for the first state, they are at around 20 of mean, and the others go to 40 up to 50 something, whereas the predictions for the current state are nearly 60. So there is something to be done there in order to correct the bias. What we did is that we started from the BIC method, which is a bias correction that I personally like very much. It's very simple and very effective. What they proposed is that they would leave the prediction scores of past states as such, and they will apply a linear layer. They will learn a linear layer to correct the bias for the predictions of the new class, of the current classes. So we can see the effect of BIC from when going from the figure on the left to the one on the right here. As I said, the past classes, depending on the state in which they were learned, they are not equal. So they have classification scores which differ on average. So we propose what we call an adaptive bias correction, whereby we learn a linear layer per past incremental state, and this is a sort of finer-grained modeling of bias correction. So now about the method. In memory-free or class incremental learning, we do not have validation data. So we do not have access to past data, so we do not have a validation set which is needed for BIC or other bias correction layers like this. So what we said is that maybe if we look at some reference data sets which can be worked with offline, so trained offline, where we have a validation memory, we can learn the parameters needed for the bias correction layer on those datasets, and then we can transfer them to target datasets, which are learn in a true memory-free CIL, so class incremental learning setting. That means that we have no access to past data. So we have two parts of the process. So we have a reference dataset training where we have validation memory. We learn everything, and then we just, when we have an actual incremental dataset, we just apply those the learn parameters. So the big assumption here is that the parameters will be stable enough to be transferred between datasets. So we'll see that to some extent this is true. So what we've done then is that we trained the framework with 10 reference datasets. So we have all datasets have 100 classes. We done some random sampling from ImageNet. We kept 500 images per class for training, 200 for validation. And then we tested this with CIFAR 100, another ImageNet subset, which is completely distinct from the reference ones, with another one which is focused on birds, so still ImageNet, and with Food 100, which is part of Food 101. We kept the classical ResNet 18 network as a backbone, and we varied a number of incremental states between 5 and 20, so 5, 10, 20. Basically, we have either 20, 10, or 5 classes per state during the incremental process. And we have, of course, the same number of classes for each state. So as I said, we tried this on top of 4 incremental learning methods which work without memory. So learning without forgetting, which is the most classical one in a way. We have Lucia, which was proposed in 2019 by Hu and colleagues. One of ours, which is Hugh, so it was proposed last 2020 at BMVC, and then FT Plus, which was proposed by Masana in his overview paper on class incremental learning. What's interesting here to note is that the first two use distillation, whereas the others, so Hugh and FT Plus, do not use distillation. So we wanted to see whether the method would work in any of these cases. So we present results with these methods, with the classical version of bias correction, so BIC, with our version of BIC, and with an oracle. So the oracle is that we look at the reference, we take the reference data set, which ensures the best parameter transfer from reference to target. Otherwise, the parameters which are learned were average. So basically, we have an average over 10 reference data sets. So first, we wanted to show, let's say, a sort of qualitative results, which is the effect of applying the method on the classification score. So we show here these results. So we have the shampoo way of doing it with before and after. So we do it for learning without forgetting and for Lucier. So on the top row we have so the row prediction scores, and on the bottom row we have the prediction scores after correcting the bias. So what we see is that the bias correction works pretty well, and particularly for Lucier, where we have scores which are on average, which have the same average for states from 3 to 10. So here again we are in the final incremental states in state 10, and we look at the mean scores per class past state and or a new state. And also the method works to some extent for learning without forgetting too, since the difference between the current state and the class in the current state and the classes from the past states is lower than before applying the method. Now, in terms of scores, I will not read them all. So what we showed here is the scores with the original method, applying BIG, applying our version of BIG and an oracle. And we, to facilitate the reading, we show the best scores per configuration in bold, and we show also the gains which were obtained. So what we can see is that in terms of basic methods, learning without forgetting is clearly the best one in all settings and for both datasets, and we have this is also the case for the other two datasets. Lucier comes second, and then we have the other two methods which don't have distillation, which have lower scores. Then once we apply BIG, Lucier gets closer to learning without forgetting, and this is even more so the case when we apply our version of BIG, so add BIG, where we have sometimes learning without forgetting, which is still better, and then BIG, which is better, Lucier, which is better in other cases. What is also interesting to note is that the effect of the method varies quite a lot. So it has a, let's say, mild positive influence for learning without forgetting. It increases Lucier scores by a lot, especially for 5 and 10 incremental states. And then it has, let's say, lower influence, but still predominantly positive for CU and for fine-tuning plus. Then we have the scores similarly for birds and for food. What's, again, best results for Lucier, and then lower for the other methods. We have double digits gains for, or in some cases here again, so for birds it goes up to 14% gains, and for food up to nearly 11%. And to conclude, we showed a quite simple way to have bias correction done in memory-free class incremental learning. We also improved the bias correction layer by by learning parameters per incremental state instead of global parameters. We still have a bit of gain to compare if we want to go towards the oracle. So we try to refine the method to get closer to it. And what we also want to do is to test the method on large-scale datasets. This is very important because many times in incremental learning, what works well on small datasets that is not confirmed on large datasets. So it's important to see what happens there. The code and the dataset details are publicly available in GitHub, and we have some references here if you need them, and that's it from my side. Thank you.
Great. Succinct and straight to the point, but really, really well done. I enjoyed that. Could you bring the slides back up? I have a few questions.
Sure.
And at this time, if anyone else has a questions, feel free to please unmute on Microsoft Teams, or if you're watching on YouTube Live, if you just enter into the chat, I will relay your question to Adrian live right now. Could you go to slide 12, please, the main results? I first want to say that I think this is it's something I never considered before, but it makes so much sense. If I'm correct me where I'm wrong, the goal is to leverage auxiliary continual learning tasks to use that as an assumption that the bias corrections and other tasks will have similar weightings. Is that great? My first question, just make sure I understand, do any of the methods in here use memory?
No.
Okay, so that's what I was wondering. How does your method beat BIC, but beat BIC without memory? That makes more sense.
So it's the comparison is fair in that sense. So there is no memory involved in any of the methods.
Right. I just wanted to clarify. Thank you. So one thing I was wondering, this may be high level and there's not really a response, but I'm wondering if there's a way to not only view this transfer as an assumption, but rather an inductive bias in a way that you could somehow tweak the method not to leverage this assumed that the transferred weights are going to be similar to here, but rather there would be some way to actually fit it in a way. And I don't mean, obviously you can't just fit a mean and variance of a score and expect that to work, but rather if you had like the mean and variances of every task hit something in both your auxiliary data, you could match that in the main continual learning experiments. I wonder if that, and then you did the BIC on top of that, if that would somehow enforce more like transferability between the continual learning sequences. I'm just thinking out loud here. I'm just wondering if in general, the general thing there, I'm just wondering out loud if there's a way to not just view this as an assumption, but rather, I use the word inductive bias, but just, yeah, a way to like leverage it deeper. You don't have to comment on that. I'm just curious.
Yeah, that's a good one, but I don't have an answer, straight answer yet.
And does anyone have on MS Teams have a question?
Hi, I have one question. Actually, two questions. On the slide 9, you mentioned Oracle method. Please explain more about that.
Sorry, what?
Oracle method.
Yeah, the Oracle. So maybe I will go to slide here. So here, as I said, we have reference data sets. So we trained, we learned method parameters on 10 of those data sets. And then, well, we've done some statistics. We've seen that they don't vary that much, but there is some variation. So I said, if we want to have something which is stable, we compute the mean values of the alpha and beta for 1 to up to the final state, and we use those means to run the bias correction method. And then in the Oracle, what we did, the Oracle was basically saying, okay, we have 10 data sets. We try them all individually instead of trying the mean values of the parameters. So we try the individual values of the parameters learned on each data set, and we report the performance obtained with the best of the 10. And as you can see in the results here, well, we get close to the Oracle with the ADBIC, so that's the good news. But there are still some gains to make if we went towards the Oracle. So one open question then is how to find a way to actually pinpoint to guess the data set which is the best for the reference data set which is the best for transferring towards any of the target data sets.
This was good. Thank you. Thank you so
much. Thank you.
And one more question: how do you compute standard deviation on slide 12?
Slide 12. Well, actually, it's not the standard deviation that we show. It's what we show there is we show the gains or the loss compared to the basic method. So it's basically the difference between the first line in each block of results.
And then big. Okay, so that is 1% gain in 1%.
Exactly. Yes.
And usually, how do we compute gain? Because in few papers I have read the standard deviation, I guess. Is it standard deviation or some other thing?
Well, in those papers, what the authors do is that they do several runs for each method, and then they show the error bars of standard deviation. So in between the results. So basically, you have a set of results. There is some variation because the training processes are not deterministic, and then you compute those error bars and you show that for, let's say, having some sort of statistically safer reporting of results.
Good.
Mm-hmm.
Thank you so much.
Mm-hmm.
Great. Are there any more questions? I have just one left. Based off your intuitions in this work, one thing I've found in my work, an intuition I've gained is that maybe when you reduce the core set, or when you have no core set, no memory, results for incremental learning seem to plummet naively. But it seems that a lot of this work, including yours, seems to show that it's not so much about the forgetting per se from the future space, but really just the bias. And when you, like in your work, you showed that when you correct the bias, you gain a lot of that back. Do you have any intuition on or does that match your intuition that when you remove the core set, you can still mitigate forgetting rather simply, but it seems to be the bias is what destroys performance? Or do you have any comments on that?
Yeah, so let's say it's quite complicated to answer. I would say it's a mix of the two, because if you look at the results compared to the joint line, you can see that we are able to correct them quite well when we have a small number of states, so for 5 states, and the picture gets much darker when we go to 20 states, and this is regardless of the data set. So basically what that points towards that you have quite a lot of catastrophic forgetting, which is in this case due to the fact that you are distilling and you are fine-tuning with distillation or without distillation, but you're basically fine-tuning a lot of times, and the model gets kind of lost in the way. But bias correction is one way to go about it. The other way, which is I think we change about this by mail in our context, is simply fixing the initial model or using a pre-trained model. And I see that Tyler is here too, so she also done some nice work on that. But when we do that, when we have a frozen initial model, many times people say that it's not actual incremental learning, and well, in a way they are right, but the results are pretty good. So especially in the memory-free setting. So yeah.
Yeah, I think that's starting to change some. I've had some work using pre-trained models. I feel like the question you should answer is, what's actually useful. And when you think in terms of applications, nobody's going to take a raw model, initialized model, and throw it out to some memory-constrained problem setting. They're probably going to have some pre-training. I've actually seen some papers. What they do, I think, to try and circumvent the naysayers is rather than have pre-training, they have a very large first task, such as train on half of CFAR 100 as your first task, and then do small task increments from there, which seems to kind of, I think, alleviate concerns from others, even though it's necessarily, or it's not that dissimilar from just pre-training with an auxiliary data set. But here we are.
It's a question of having something pragmatic versus having something which is easy to accept by the reviewers.
So the best answer, have both.
Yeah.
Great. If there are no more questions, I guess we can wrap up at this time. Thank you, everybody, for joining today, and thank you, Adrian, for this wonderful presentation. Don't forget to consider joining ContinualAI as a full member. For more information on how to do this, you can either visit the link that's posted in both the description of this video on YouTube as well as the live chat. You can catch us again next week at a different time. Our speaker is speaking from South Korea, so we will be chatting at 12 a.m. UTC or 2 a.m. European Summer Time. So I imagine many in attendance may be not able to join live, but many who are having to watch these at a later time on their own because it's at such a late time may be able to join live next time. We'll hear from Jung-Yoon on his work on realistic setups for continual learning. So it'll be very exciting next week. And again, it's a different time that may help some others. So I guess we'll see most of you then, and have a great rest of the week. Thank you.
Thank you. Bye bye.